So this talk I've kind of titled Portable Distributed Systems, or what if we put Node.js on routers? I should put quotes around that, routers. Or how I accidentally became a Linux network admin for an open source hardware project. Doesn't really quite roll off the tongue as the other ones, but wanted to throw that in there. Florida explained a bit about me. I am first and foremost trying to be an empathetic community member, whether it's part of a software project, hardware, or just part of organizing meetup, or just anything I'm involved with. I am a steering committee member for the Tesla project, which I'll dig into a bit more later in this talk. I'm a contributor to the Hoodie project, which is a lot of my inspiration into what I want to do with open source. I'm co-organizer of Manhattan.js, which is a fantastic member of the Borough.js family. So if you live in New York or visiting, there's usually at least one JavaScript meetup each week. So just look it up, and they're a lot of fun. And professionally, what I actually get paid to do is to be a front-end developer at a company called Namely. And so I'm here today, and I'm really excited that Will was kind of the person right before lunch and leading up a lot of good transition into what I'm speaking about, a bit about conference Wi-Fi and tech demos. If you've ever attended a conference, some kind of technical event, and you've seen someone do a demo that relies on outer internet connection, sometimes that doesn't always work out so well, especially if people are doing like BitTorrent or something like that on the network and bring it down, or just streaming or NPM installing. Like it happens to the best of us. And especially at a conference like EmpireNode, we find that people who do Node love real time. When I was first learning about Node.js, a lot of the resources I found online were talking about the real-time web and Node.js, like Socket.io, let's do it. And you see a lot of these dev setups for these awesome demos of like, this is from like Google Cloud's documentation of like, okay, we have a game screen that's on your laptop, and we have a game controller that's on your phone. But you have these other servers out somewhere else that are running all these requests, and even though you're literally like a foot from the surface, it's going to take that round trip in order to get there. And it's interesting to me, and it might work with a really solid connection, but that's not always the case, as we might see from, has anyone seen the clip of Steve Jobs at doing his tech demo and telling people to turn off their Wi-Fi? Here, let's.
570 Wi-Fi base stations operating in this room. Okay? We can't deal with that. So we have two choices. Either I've got some more demos that are really great that I'd like to show you. So we either turn off all the stuff and see the demos, or we give up and I don't show you the demos. Would you like to see the demos or not? So here's the deal. Let's turn up the lights in the hall. Several hundred of these Wi-Fi bits too, by the way.
All right, we'll keep going from there. It's just basically him berating the audience to basically police each other to turn off their Wi-Fi and their laptop and everything like that. And it's 570 Wi-Fi base stations couldn't hold up that audience, and the tech demos were falling over because basically two big things that we can deal with in real time. It's bandwidth and latency. You may have heard these terms, may not know exactly what they mean. So basically, bandwidth is that amount of data that can go over some kind of pipe, some stream. Can also be thought of like megabits per second. And bits is important. A lot of people, bits and bytes, it's very different things. And then latency is that time between connecting from a client to the endpoint, which could be a server. At this point, it's a client, this is a laptop, and it's trying to connect to a server somewhere on another part of the world. And what's getting transferred over that is usually what are called packets. This is kind of what the header of a packet looks like. This is all kind of this source information that these networks need in order to kind of know where it's going, how big it is, what's coming next after it. This is very important for kind of what leads into the major cause of these tech demos falling over in real time is latency. And latency is made up of like 4 different types of delays. So we have propagation delay, transmission delay, processing delay, and queuing delay. And each packet traveling over the network will incur many instances of each of these delays. So breaking them down a bit, propagation delay is the amount of time required to send a packet from the client, let's call it in this case a router, to a server. It's usually dictated by the distance and the medium, depending on like what the copper or fiber or whatever is made out of, through which the signal travels. And usually the propagation speed is usually within a small constant factor of the speed of light. To give a real-world example, the round-trip time, or RTT, if you see that around, over fiber from New York to San Francisco is around 42 milliseconds. Now, that's not super like speed of light maybe, but that's something to take into factor when you're trying to deal with, okay, I'm doing a server request to something out in San Francisco. Think about over in Japan or Australia. That's just adding up over time. And then we have transmission delay, which is the amount of time needed to transmit all that data in the packet over the wire. This is the rate at which it goes, rather than the distance. Processing delay is the amount it takes to process the data packet's headers that we saw before and determine its target destination. This is a very minimal delay, but it still occurs nonetheless. And then, of course, queuing delay. This is the most significant of the delays in our conference Wi-Fi situation. In times of high traffic, we run into this occurrence of what's called buffer bloat. It's the undesirable latency that comes from a router or other network equipment buffering too much data. That underlying problem is that many routers are now shipping with large incoming buffers under the assumption that dropping packets should be avoided at all cost. This introduces high and variable latencies delays into the network. The higher the load of the traffic along the path, the higher the likelihood that our packet being queued and delayed inside one of our buffers, in one or more. So it's all building up and then just staying there until it can process them all because it doesn't want to lose any of it, which results in us looking at a page until 500 is on us, basically. And we can actually track and measure some of this latency. There's a tool called traceroute or traceRT on Windows. And this is an example from google.com. This is one of the fastest sites on the internet to load, right? If you're even google.com, it takes about 23 hops from the router to getting to that final destination to respond back to us. And that's very minimal now on a constant network, but that can add up over time. Take, for example, we have the traceroute for github.com. There's only a maximum of 64 hops allowed for traceroute, and it times out. And it takes quite a while. So think a little bit about that latency that racks up when pushing commit to a GitHub repo during a conference or downloading another Git repo and cloning while you're sitting out in the audience. And one of the studies by the creators of Spidey, or SPDY, Speedy, who knows? We can see the impact on page load times when bandwidth is increased versus when latency is decreased. And it's kind of incredible. Eventually, we start like kind of leveling out on bandwidth. But latency, the more you drop it, it still ends up improving our load times. Basically, for every 20 millisecond improvement on latency, we have a linear improvement in page loading times. And that's really how we can gain dramatic improvements on load times. And my biggest idea for doing this is basically cutting out a bunch of those middle points and putting our apps at the first point of the request. What about routers? Now, this idea didn't come out of thin air. There's some prior art and inspiration that came before this. One of the great ones that really kicked it off for me was a project called Subnodes. I saw at Brooklyn.js. Sarah Grant presented the project, and she was showing how she set up a Raspberry Pi to run a Node.js chat application and serve a local area network, or LAN, for anyone in the room to connect and start chatting. It was awesome. We were all sitting there in the upstairs bar of 61 Local and just chatting with each other on this cool little app she made. And it was all very local. No one outside the room could do it, and it was awesome. And then a couple months later, I went to Disneyland. I'm a massive Disney fan, Disney parks especially. And it was my first time, and I was really looking forward to this show called World of Color. And before the show, everyone can gather around the kind of lagoon that it's going to be taking place at. And they serve a local network there called Peer Games. And you can play a pattern matching game that's served from that from that game, or from that network. A little bit like Simon. And you have the ability to control the color of the gigantic Ferris wheel in front of you if you win the round of that game, which is kind of incredible. You win this game, you're sitting out there, and you get to control the colors in front of you with this massive piece of hardware, basically. And it was amazing to see kind of a real-time interactive experience isolated to just one area of this park and this environment. So it gave me these two inspirations. I wanted to explore this possibility of building out this type of experience, localized, real-time, interactive, without the budget of Disney, and the ease of use of any typical Node.js development environment. Because one of the biggest things that when I viewed the Subnodes project was that flashing a Raspberry Pi, getting a couple of Wi-Fi dongles, and setting up the shell script was kind of a lot just to get started. And it was stuff I didn't really understand when reading through the code, so it made me a little uncomfortable. And that's kind of where the Tesla 2 comes in. I'm biased because I work on the project, but it was before I found this project that really got me into it. The hardware itself, these are kind of like the breakdown of it, but ideally we have this MediaTek chip, which is our system on a chip. So basically it's running Linux. And also has an Atmel SAMD21 microcontroller chip, which is kind of our really nice performant GPIO to the hardware. And on that chip, the MediaTek, we're running a modified version of OpenWRT Linux. And if you check out OpenWRT, it's called an embedded Linux distribution. But when they mean embedded, it usually means routers. Like I found it mostly on routing devices. And it's kind of incredible to see how much it's been distributed across all these devices that just live in our homes, and we may not have any idea about it. So I started exploring the Tesla project, and the tooling around it was absolutely incredible because you have the CLI and firmware that lives on it that you can require a node module that just lives on the device and start controlling the bits around you. You can connect to Wi-Fi, push code over, and without having to do anything like SSHing into the device or running NPM on the device even, or installing Node on the device out of the box. Hello world, being blinking LED on the board in less than 5 minutes, which was very impressive to me. But one thing I was missing when I first started with the project was the ability to create that local network that I kept seeing, access point, as it's also called. And it was something I needed to make this idea a reality. So, it being an open source project, I helped implement it. I added it to the CLI, and then eventually added it to the Tesla node module that lives on the device. So you can require Tesla and start controlling networks, disabling, enabling them, resetting, do whatever you need to do. And this was really awesome to be able to contribute this way and kind of see my dream come true and helping others take advantage of that by sharing it. And eventually I started creating a router on a router. It's basically the simplest app I could create to spin up an access point, serve a web page from it, because that's the other thing. It's running Linux and Node. I can run a web server and serve from this device, and then people can control the hardware on Tesla from a web page. No native apps, no Bluetooth, just simple HTTP and Wi-Fi. So any device connected to the Tesla can get served this data that I was serving out for it. And remember we talked about latency. Check out the trace route output. One hop, then we're done. So this is all great for reducing that round trip time, but one tiny Tesla, even though a router can take us to the moon, this tiny Tesla may not be able to serve that room that 570 Wi-Fi base stations couldn't serve. So how do we, distribute this load? How do we scale, as people like to talk about? We could have just one main contact and have a bunch of other Wi-Fi access points of Teslas, like kind of subscribing to it almost, like just kind of listening for pings from it. But that doesn't really spread out too far when we get too far from our main device. It doesn't match this idea of distributed systems that I was talking about earlier, where any node can drop and the slack is picked up by anyone else in the network. And that's where we get into MAN-A. Oh, shit. Mobile ad hoc network. So Basically, a mobile ad hoc network is a continuously self-configuring and infrastructureless network. It's a mouthful, I know. But really, it's devices configured to an ad hoc network will be a connected node and an emitter of that network simultaneously. So there's no one point of failure in the system. The network exists as long as there's at least one node emitting, and then it's gone after they're all spread out. And so I think of Tesla as quite mobile because it fits in my pocket. So I would say it kind of fits that definition. Also, one thing, the internet can't seem to agree how to phrase ad hoc one way or another, so you might run into a few different types of phrasing. And the great thing is OpenWRT supports ad hoc out of the box. So where does Node come in? So we have this ad hoc network running around, but tools such as HTTP and even TCP doesn't really work for this type of environment. Remember we talked about sockets before. Who's used the dgram module before? Can you raise your hands? Very sparingly. All right, cool. I found that out as I was trying to research more about the dgram modules. There's not much out there about it and how to use it. And so it's the Node.js implementation of UDP, which is User Datagram Protocol. And it's kind of been around for a while. It was originally designed in 1980 and is now one of the core members of the Internet Protocol suite. It's message-oriented and connectionless. So basically, there's like TCP, you create a connection, there's some handshakes, and you have that connection open, and you can start communicating through that. This just kind of says, you know what, here's some data, go for it. I don't care if you need it or not, but which makes it faster but less reliable than TCP because you have no guarantee that it will actually make it there. Just hope that you send it out and someone catches it. And this protocol is used by DNS and DHCP. DNS being a domain name server. And DHCP, do not remember the acronym for that, but it's very important for your kind of firewalls and routing and catching domain resolutions and distributing IP addresses as well. And as part of this dgram UDP module, we have MDNS. Who's ever seen MDNS responder start fouling up on their computers? Yeah, maybe a few. So this is what that's about, multicast DNS. It's described as a zero configuration service, or zero conf. It was designed and proposed in 1997 by an Apple engineer named Stuart Cheshire. And it works to resolve host names on a distributed network, basically, without the local name server. So there's not one point that's be able to resolve that. They all have a way to resolve it themselves through this multicast DNS. And it's used in conjunction with a tool called DNS-SD. And then DNS-SD is implemented in Bonjour, if you've all seen a Bonjour on your Macs, or Avahi, I think is how you pronounce it, for Linux. Windows, unfortunately, does not have an official client for this or support. Supposedly, Windows 10 has it built in or is coming soon. But if you have like iTunes for Windows, it'll work for you too. That's used by Safari, iChat, Messages. It uses these DNS records to advertise instances of service names. And that's exactly how Tesla discovers, or the T2 CLI discovers Teslas on a network already. We have the service type called _Tesla._TCP, and then we have the instant names that we can catch and start discovering and working with. So we can see that MDNS.js, we have a pure JavaScript version that will work on cross-platform, but also on our device itself. We can discover other Teslas within Tesla too. And then we can start distributing these networks around and communicating across it without having to have one central point. Now, there's some caveats with the system. Constrained space. We have 64 megabytes of RAM and 32 megabytes of flash. That's not a lot. So you have to be a little stingy sometimes with your node modules and how you just work with some data. Discoverability is also a big thing. It just shows up under under devices on most platforms. And when you try to connect to it, it says it's not connected to the internet. Are you sure? And I think a lot of people are going to kind of like scare away from that when they see it. And it also requires a static IP address. So it's like that whole setup is not very user-friendly when compared to regular Wi-Fi networks, which is why usually you want to have an extra probably Wi-Fi dongle in order to serve a separate access point and just use that ad hoc network to communicate between devices. So knowing all this, I know it's a lot to take in. Do we dare to demo? Yeah? Can I get? Yeah? All right. So the first thing's been running this entire time, a local live stream. So if anyone's seen the little webcam sitting here, I have it served across the network right now that you all can connect to. It's using a library called TESLAV, which Rick Waldron, thank you for all your work on this and making it super performant and awesome to use. So if you find an SSID called Tesla Live Cam, you can connect to it using EmpireNode. And any of these network DNS domain names will work. Tesla.com, TeslaCam.com, TeslaLive.cam, EmpireNode.org, just to prove that that works. Let's see, let's refresh. Hey, look at us. So we have our Tesla Cam, and we can say, I can't say, oh, dang it. Hold on. Ta-da! It's massive in my head. Oh, shoot. All right. So we have the Tesla Cam. Let's point at the audience. Hey, nice and blurry. Nice HD camera. So we have our live Tesla Cam, and this will come in handy for the next demo, if I can. And that demo being, so yeah, I tweeted this out the other night, and obviously hijacked the, God dang it, I didn't. Hey, there we go. So I've hijacked the DNS resolution for EmpireNode.org and to show my app instead. This is kind of a good time to warn about connecting to unknown wireless networks. Always use a WPA2 encrypted network. I like that iOS now warns you if you're using something lower than that. It says like security warning, just make sure. But even then, the network admin has a lot of control over the network. Like I'm serving WPA2, you connect to it. I stole EmpireNode.org. I could serve a sample application and catch passwords if I really wanted to. I'm not, because there's no password input, but just to be fair warning out there. Including, if everyone's ever heard of the upside down internet, some person found out their neighbors were stealing their internet, so they started filtering out their traffic and turning all images upside down. It's completely possible. The second thing is the Tesla Mobile. It's this little kit I put together first for the NYC Node meetup in New York. Serve a little web app from it, and have an open source project that you can check out. So we're going to check that out now and see how that works. Can you all see? All right. So we have the Tesla Mobile, nice frame rate. All right, down. There we go. Oh, that's janky. All right, I'm just going to serve it. So we have the Tesla Mobile up here. I'm going to put it down. I can't really see down here. I'll just keep it on the table very carefully. So I have my iPad connected to the Wi-Fi network, still, ideally. So we got a little control. Let's speed up a bit. So I don't have a native app. I don't have any sort of thing. And there it goes. And it's resilient if it stays connected. And it's dead. All right. All right, hardware demos, everyone. The last demo being, real quick, Tesla Comms. So this is the one thing I was trying to get done this past month, getting prepped for EmpireNode. And if I can have Suze Hinton in the audience and Florida out here to help me out. So I have these simple, basically button and LED. So Suze, you're gonna, if you can step right in front of the table here, and then here you go, Florida. Just trying to make sure the wires don't come unconnected. It's a really solid setup, you can see, kind of just spare batteries and stuff. So in the middle of the stage 2 as well works. So the idea is we have an ad hoc network running on all these devices, and we have a button. When I press the button, it should emit a broadcast, basically a simple pub sub. We're going to push out basically an event with some data that says, all right, turn on the LED, or turn it off, toggle it basically. And when I press it, all the LEDs should go on. Okay, so hey, there we go. So now this is all wireless. Anyone can drop on and come back on in order to subscribe to this event. Now, if Florida presses the button, they turn off. Coming on and off because we're controlling it. And now we can subscribe to any sort of type of stream. We could use that RxJS that Justin was talking about earlier and start and start managing this. And I could have this spread out around, eventually hopefully streaming video through this type of network. And it's just there. It's so much fun to play around with, but I'll tell you, I figured this out yesterday afternoon. Finally got it working in order to multicast this type of events. Yes, anyone who can attach to this network can start listening to those events too, but you can also secure your ad hoc network too. So thank you very much for helping me out with that. Yeah. I only have a very little time next. So what's next after this? We have this ad hoc stuff. We have these connections, this portable distributed network. Well, I think one thing that's big in my life, as I talked about with Hoodie before, I'd like to get PouchDB and PouchDB server running on this. Let's get some syncing between these devices using, you can push a database onto an SD card. That's what I love. You can just use SQLite, push it onto an SD card, and have a backup. You can start doing real applications on this type of stuff. I'm planning to work with Batsley Adams, Andy Ritano, in using his NES Spectre project and taking out all this stuff from the cloud and even removing the PySerial script and just having a Tessel embedded in his NES. That serves its own little network, does straight up serial control to the device in order to control and kind of be the ghost in the machine for his projects. And it should be fairly simple with these type of stuff set up. I see some nice stuff in the future coming out. I think that Google should really combine their two new devices that they have for the home into like Google Home Wi-Fi or something. Because the whole voice control and then the Wi-Fi router being separate, it doesn't make sense to me right now. It's like just serve an app and then control all that data within the device itself rather than pushing out to remote servers, which can increase latency and also, I don't know, maybe feel people more secure about their data. A cool project is coming out along those lines called Daply. It's kind of most similar to the idea that I'm working on with Tessel. Control over your home router that can also run applications on the device. And they're doing a lot of great work in the open to make kind of encrypting, serving HTTPS and SSL stuff on the device itself, and creating this environment. And overall, this biggest thing has taught me Linux networking for web developers, basically. Accidentally became that go-to person for the project to debug and develop network functionality, but I'm still learning a lot. And it's a lot of subjects that many people in the network admin industry take for granted. DNS masks, DHCP, MDNS, all these different things that I would never know what to look for, either because they're unique to OpenWRT or they're general to Linux by itself. And trying to discern those things can be frustrating for someone coming from a world that's searching for a concept or a bug, comes up with tons of resources and tutorials. Node and JavaScript are fantastic for this. We just have to find those resources that make it better. So I'm starting out with this book, and a lot of my resources for latency and bandwidth came from this awesome book you can read for free online, and then also buy the book if you want to as well. If you want to learn more, here's some Tessel.io. You can find me on Twitter at hipsterbrown or ping the Tessel project. We have a great open Slack. Let's go full stack to the metal. Thank you.
Thank you so much, Nick.
Yeah.